Welcome to the last part of electrons. And this is where it gets a little intense, but not really. It just kind of ties everything together. And we're going to start off with Mr. Schrödinger here, Heisenberg's partner in finalizing, at least for now, who knows what the future holds, but at least for now, the modern model of the electron, okay? It's called the quantum mechanics model. And in that model, and we already knew this from previous scientists, but atoms have a dense, positively charged nucleus. Electrons surround the nucleus and are treated as waves. And electrons live in this 3D atomic orbitals, that lie within energy levels of, and this is the final part, the electron cloud. Now, we did talk about that a little bit in the atomic theory unit, but we're going to take it next step further. So this, I believe, is in your notes. If not, yeah, I think it is. You just have to label it. So obviously the nucleus is in the center and the electron cloud is around that. And we talked on the previous set of slides that talked about how the probability of finding the electron in an orbit is related to this cloud, okay, the present day model of an atom. But you have to think about it this way. I think we've all seen, at least on TV, well, here's a picture of it anyway, if you haven't, a propeller blade. You could probably go down to Davis Island and sit there for a few hours and at the airport or across from the airport and wait for an airplane to take off and see this in reality. But the propeller blade, right? As it's spinning, it has a blurry region. It's spinning so fast that you don't know where the blade is at any one instant, okay? So the electron cloud is very similar. So in other words, this quantum model determines the allowed energies of an electron can have and how likely it is to find that electron in various locations around the nucleus. So we know that there's a propeller blade there. Just like in an atom, we know there's an electron there. And we can probably guess as to where it is at any given instant, but or how fast it's going, but we can't know both. So the quantum mechanical model gives us that probability that I mentioned before of finding an electron within a certain volume of space surrounding the nucleus. And that volume of space is represented as a fuzzy cloud in a model. Now, this image that you see here on the screen is still only two-dimensional. And it doesn't quite show these orbits. And of course, it's not to scale. A nucleus is by far much smaller than that. Remember the Raymond James model where the nucleus was ahead of a pin at the 50-yard line and the electrons were way out in the upper nosebleed section, meaning that most of the atom was empty space, right? All right. So several times now we've referred to this fuzzy cloud, but that's the cloud model. So where the cloud is densest, the probability for finding the electron is greater. And where the cloud is least dense, the probability of finding the electron is less. And these are called density maps. You just have to recognize them. You don't have to know how to read them or anything like that. So that's good. So as you're aware, but maybe you don't think of it very often, we live in a three-dimensional universe, not two-dimensional. Look at the desktop that you're taking notes on right now or sitting at. That's a two-dimensional surface. It has a length and a width. But if you just turn your head a little bit sideways or glance over at your neighbor's desk, you can see that there's also a thickness or depth. So there's length, height, and depth. And we call these dimensions X, Y, and Z when we are referring to the three-dimensionality of an atom. So if you can imagine this line right here coming, this part going back into the screen and its corresponding end coming out of the screen. And going back here and looking at this line now, this one coming out of the screen toward you, but to the left a little bit. And then this one going back into the screen. And then this one just going straight up and down in the center of both of these three-dimensional. So that would make this shape a sphere rather than a circle, right? This electron cloud version of an atom. And this is called a probability cloud. Now, if we fill it in with more of an opaque or a translucent shape, spherical shape, we know that this orbital shape is an s orbital, okay? And there's a 90% chance of finding an electron within its orbital at any given time. So again, these are models. Models are never perfect. But they're the closest we have to a visual representation on a flat screen, okay? So these s orbitals, like we said before, are spherically shaped. Smaller s orbitals will have smaller spheres, and larger atoms will have more electrons, so their s orbitals will take up more space. And it also depends on the energy level. A 1s will be far smaller than a 3 or 4 or 5s. And all s's are this shape, spherical. P orbitals are very different, aren't they? This one, and virtually all of them, are dumbbell shaped. And I'm going to show you what they all look like in each of their dimensions. So here you have one on the Z. Remember I said X, Y, Z. Those lines can be labeled X, Y, Z. And this one's a little better representation because the larger these are coming out at you. You can imagine like being in a 3D movie and, you know, these coming out the screen and these going back into the screen and then this going up and down vertically. So this is your Z axis, the up and down, X axis, and Y. So we'll start over. You have your Z, X, and Y. These are your p orbitals. And each of these dumbbells represents 2 electrons. How many electrons can fit in a p orbital? 6. 2 in each of these shapes. So when you have 2p2, 2p4, 2p6, that's what 2p6 looks like, okay? This is all 3 of the orbitals, the p orbitals put together on the X, Y, and Z axes. Yes, that's how you spell the word plural of axis. Looks like the word axes, like chop chop wood, spelled the same, pronounced differently, pronounced axes, okay? And this is the shape of a p orbital. Pretty interesting and very three-dimensional. Now here are other shapes of the orbitals. You've got, we already said S, here are the 3 p orbitals, here are the d orbitals. So the d orbitals are kind of like double p's in each dimension, okay? And then you have this oddball one, the 5th one, because remember in D can hold 10 electrons, 2, 4, 6, 8, 10. And here, this dumbbell looking one is 1 electron going around in like an infinity sideways 8, and then the other one's going back and forth in and out of the screen in a, you know, loop-to-loop infinity sign. And then here, one electron's going around and around and around like that, and another one's going around and around and around like that. And if you put them all together, you'd have a full d orbital, 2, 4, 6, 8, 10 electrons. So you can imagine all of these electrons interacting together and flying, virtually like at the speed of light around their nucleus. How hard to keep track they would be. And then here are your f orbitals, and don't even worry about those. They get rather complicated, and we do not have to know too much about those right now. Really, we don't have to know too much more than the S and P shapes, okay? And then here's kind of all of it in one kind of neat package. You've got your energy levels over here. You've got your orbital names, S, P, D, and F, their shapes, and then where you'd find them in, so 1, 2, 3, 4, and how they correspond to the different shapes here, okay? Stacked orbitals. So if we put first and second level s orbitals together along with the second 2p orbital, this is what an atom would look like, roughly, with its shape, the shape of its orbitals, okay? So you see the inner sphere, that's a 1s, and it's full, so that's a 1s2, going back to our last notes. Then you've got 2s2, this is your energy level 2s, and then what comes next? 2p, 6, and this has all 6 filled out, so that's, so how many electrons is that? That's 6, 7, 8, 9, 10. This is neon, 10 electrons. And here it is labeled, 1s, 2s, and the 2p dumbbell shapes inside, all together. So, and here's a even more complex one with possibly a higher level s on the outside, and even some d orbitals thrown in there. Okay, so these electrons are going all over the place. But remember, only the valence electrons are the ones that take place. The outer electrons take place in chemical reactions. Okay. And so you have a question in your notes that's asking you why atoms are spherical based upon all the evidence that we've collected in our notes in this class so far. You can probably explain now why atoms are spherical. And here's just a different look at it. Okay, different atomic orbitals are denoted by letters. S's are spheres, P's are dumbbell, and then the 5 D's have just dumbbell-shaped orientations for 4 of them, and then this oddball one with this weird electron pair going around in a circle down or through the center. It's pretty interesting. So now you have this chart to fill out, okay? And it tells the numbers and kinds of atomic orbitals and their sublevels. So you're going to fill out the energy level, N, which is 1, 2, 3, 4. How many sublevels there are, the letters S, P, D, F, speed fast, right? S, P, D, F. The number of orbitals per sublevel, the number of electrons in each orbital, and then the total electrons in each energy level. I'm going to have you think about that. I'm not going to display the answers for you right now. They are on this video. So at this time, I'm going to turn this video off in class. But when you revisit these notes before the test, you'll be able to see what your answers are because they'll be the last slide on this presentation. Okay, so I'm going to turn it off right now. And for those of you revisiting, here are the answers. So here are your energy levels, your number of sublevels or shells, the letters. So in 1, there's S only. In 2, there's S and P. In 3, there's S, P, and D. In 4, there's S, P, D, F. And then number of orbitals per sublevel and electrons per orbital and the total electrons in an energy level, okay? Disregard that 75, that is the slide number, not an answer to this chart, okay? All right. Any questions? Let me know.